Effective team training is an essential part of our sustainable growth strategy. This tally shows the skill level of each member for each selected tool. The expertise ranges from 0 being the lowest to 3 being the highest. This is the change that was observed throughout the year. We have a collaborative and unstructured teamwork environment where the more experienced members train the newer members. By summing the total team skills for each category, we can clearly see the improvement that the team experienced. The largest improvement was in electric wiring, and the least was in ANSYS product simulation. In this bar graph, we see a shift in the team's expertise from level 1 to levels 2 and 3 towards the end of the year. As for our mechanical system, the fuselage is made out of balsa wood and plywood. The wing has a 2-degree positive dihedral angle for more stability with a spar semi-monocoque made of balsa wood structure, having a torsion box with a spar made of composite material and covered with monocoat. The single boom is made out of carbon fiber, the tail out of balsa wood. The stall speed is 5 meters per second, the cruising speed 15 meters per second, and the max speed 24 meters per second. As for the electrical system, it consists of an imaging system, an obstacle avoidance system, and an autonomous system. The autonomous system consists of the autonomous takeoff, waypoints, search grid, autonomous landing, and networking system. We are highly confident in our autonomous aspects, air delivery, obstacle avoidance, and waypoint accuracy. On the other hand, we're less confident in our imaging performance and even less so in the detection and classification and localization performance. This is our gimbal test without the RC. The camera is fixed onto the gimbal, which is fixed onto a plate. We manually simulate the motions of the aircraft such as pitch, roll, and yaw. From this test, we see that the downward camera is in equilibrium at any instant of the flight and in case of any aircraft motion. As for the gimbal test with the RC, we use the RC for a wider image capture such that the gimbal could be oriented freely in any direction. From this test, we see that the camera is stable during any motion of the aircraft. For the motor testing, we fix the motor onto a wooden plate and link it to a device that measures the propeller's thrust, the battery consumption, as well as volts and amperes. This is the wing loading test, where we put rocks on top of the wing to check the strength of the wing and the maximum deflection that could happen to it. We consider the hand launching technique a type of autonomous takeoff because we use flight mode auto immediately as the plane is released. It functions using the drone kit library. We tested the autonomous flight 7 times with a total flight time of 50 minutes with only 8 minutes in manual mode. We can also carry out autonomous landing by using the autopilot, which depends on the commands of the mission planner that can be controlled by Python scripts, including the drone kit library. We gave commands to the mission planner in the shape of waypoints, which can be reached autonomously without any interface from the RC. We tested this 13 times and attempted 130 waypoints. hitting 110 of them, giving us an average miss error of 15.4%. A set of waypoints, obstacle positions, and geometry are received from the interoperability server. On this data, we apply our modified version of RRT algorithm and send the commands directly to the autopilot through math proxy. We used Unity 3D as a platform to build our mapping system to monitor the current state of the UAV in real time. We tested this flight 3 times. The total obstacles tested against were 38, and we avoided a total of 36, giving us an average collision rate of 5.26%. We control the camera and shutter rate from the ground station, and the images captured are sent through LAN to the imaging computer for processing. The images are automatically filtered, and selected images are cropped and then fed to the deep learning model. The analysis of these pictures are shown in the ODLCs. The air delivery has been tested before, where the payload was dropped and did not survive the landing as required. It landed 60 feet from the target location. Several times throughout our mission testing, we would find flaws in our system. A flaw in the autonomous flight required the team to tune the PID parameters. Also, due to a lag in latency, collision with the moving obstacles happened several times. We had to create a predictive model for them. Other problems that showed up during the detection, classification, and localization, as well as air delivery, were also solved promptly. Regarding our expected scores, we expect good results when it comes to autonomous flight, waypoint capture, waypoint accuracy, obstacle avoidance, and air delivery. Dynamic obstacle avoidance has caused problems for us, but we're expecting our performance to improve during the competition. We're expecting scores of 80 and 92% for shape classification and color detection, while character classification, orientation detection, and localization are expecting slightly lower scores.